Hello and welcome to our first lesson of chapter 5, which is integrals. This is the third big idea in our calculus course, the first being limits, the second being derivatives. In this chapter, we will learn how to compute an area under a curve, and in that process, we will be looking at integral calculus and how we can use integrals to solve problems. So just a little reminder, if we have d dx of x cubed, this means please take the derivative of x cubed, and the answer to that would be 3x squared. Now, if we wanted to go backwards, we would say the integral of 3x squared dx is equal to x cubed plus c. 3x squared dx is our integrand, and again, we read this as the integral of 3x squared with respect to x is x cubed plus c. The dx tells us that we are doing this with respect to x, similar to how when we do our derivative, the dx on the bottom of the dx tells us we are going to take the derivative of x cubed with respect to x. In general, if the derivative of big F of x equals little f of x, then the integral of little f of x is equal to big F of x plus c, where c is a constant. Big F of x plus c is the antiderivative of little f of x. So in other words, if I take the integral of little f of x dx, we're actually finding the antiderivative of little f, which is big F. The derivative of big F is little f. The antiderivative of little f is big F. So if I take the derivative, I get here. If I undo the derivative, I go back to here. Integrals and antiderivatives can be used to find the area under a curve. Now, sometimes you will have numbers at the top and the bottom of your integral sign here and here, and sometimes you will not. If you have numbers there, it is a definite integral. If there are no numbers there, then you have an indefinite integral. If there are numbers, then you can actually evaluate this to equal something like a number. If there are no numbers, then you will get an expression for your big F. All right, we're going to try some questions because this usually makes a bit more sense once you've gotten to try a few. There are two different methods we can use to find our antiderivatives. Our integrals. One is antiderivatives, and one is using what's called the area method. Okay. So if I look at this function, I have the function f of x equals 2 here. Okay, that is this horizontal line. And I'm looking at two x values. The x value is 1, which would give me a vertical line, and the other x value is 5, which gives me another vertical line. And we can see that this encloses an area here that is enclosed between our function f of x equals 2, the x-axis, and these two vertical lines where x equals 1 and x equals 5. Now, we can just use regular old area to figure out the area of this. We know the area of a rectangle is equal to length times width, which in our case would be 2 times 4, which would give me 8. Okay? This would be the area of the region here. Now, if I think about this in terms of integrals, we know that big F of 5 would be equal to 10 plus c. Big F of 1 would be equal to 2 plus c. Now, how do I know that? Well, if little f of x is equal to 2, the antiderivative of this, big F, is equal to 2x plus c. The derivative of big F would be 2, which is little f. The antiderivative of little f would be 2x plus c, which is big F. Now, if I do f of 5 minus f of 1, I get 10 plus c minus 2 plus c, which gives me 10 plus c minus 2 minus c. our c's end up canceling out, and I end up with 8, which is also my area of the region. This is called the antiderivative method, which we will be looking at further later on. Today, we're going to look at the area method. Now, in order to do the area method, we're going to be looking at a couple different methods here. One is the left-hand method, right-hand method, and midpoint method. But in all of these, we're going to be drawing some rectangles. Okay, so if I have this function f of x here, okay, that's this curve that we've got going on here. And we're going to evaluate from some x value a to some other x value b. I can't find the area of this using regular geometry because it's not something that we know the formula for, like a rectangle, like we did above. But we could break this shape into rectangles and get a pretty good approximation. For example, I could draw one rectangle right here, and another rectangle here, and another one here, and another one, and another one, and one more. And I would get a pretty good approximation. You can see we've got a couple gaps, like we've got one here, 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 and then we've got a little bit of an overlap up here in this top left corner. But this is a pretty good approximation of what the area under this curve would be if I could find the areas of each of these rectangles and add them together. Now, these ones that I drew here have what are called right endpoints because the right top corner of the rectangle is on our curve. This other one, I'm going to show you what if we did left endpoints. So if I drew the top left corner of my rectangle on my curve of each rectangle that I'm going to draw, we can see that this one here, we've got, again, some pieces where we've got a little bit extra here, 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 and here. And then we've got one where we've got a little bit under. So this one would be a little bit of an overshoot, but again, we'd be a pretty close approximation to our area under our curve. So when can we do this? So first, f of x needs to be continuous, and for now we're going to say non-negative. Okay? If we want to find the area under the curve on the interval a to b, okay, we can use this idea of breaking down into rectangles. Okay? There's going to be two methods total that we use, rectangle method, antiderivative method. Rectangle methods today, we will do the antiderivative method later, which will be the more common method you will use to solve integral problems, but the area method is another way you can do this. Okay. So if we think about this rectangle method, if I draw my rectangles, I'm going to use a right endpoint here. If I draw in my rectangle, and another one, and another one, when we draw these in, we want them all to be the same width. And we're going to call this width delta x. So obviously I'm using a little bit of eyeballing here to draw mine. But each width of each rectangle here is going to be called delta x. That's because we're going to start with a is going to be our x0, and then this x value here would be x1, and then x2, and then x3, all the way up to our final x at the end. Okay. Now if I look at rectangle number 1, what is the height of this rectangle? Well, the height of this rectangle would be wherever this point has landed on our curve, which would be f of x. So if I draw myself just this rectangle number 1 here, it's going to have a width of delta x, and it's going to have a height of f of xi, right? In this case, x1. Okay. Now, the notation we're going to see here, because we're going to have right endpoints, which we just drew, left endpoints, and sometimes midpoints, This corner here is corner A, and this corner here is corner A plus delta x. So my right endpoint is going to be f of A plus delta x. If we had a left endpoint, this would be f of A. And that's because if we had a left endpoint, my corner would have been right here, and I would have drawn in my rectangle like this. And so my height would have been different. It would have been down here. And this would have been at an x value of A. So the area of one rectangle is still length times width, but in this case, my length is f of xi, and my width is delta x. The total area of all rectangles will be the sum of all these things added up. So this would be delta x times f of x1, because we're on our right endpoints here, plus delta x times f of x2, because in this case, my height here, or my second rectangle here, would be f of x2, plus delta x is f of x3, etc., all the way up to delta x times f of xn. And b would be xn. In other words, this is going to be the sum from I equals 1 to n of f of xi times delta x. And that delta x can go in front of the sum because that delta x is going to be constant. The width of each rectangle is going to be delta x. It's always the same delta x. And you can determine this by taking your endpoint to the right, subtracting your endpoint to the left, b minus a, divided by the number of rectangles. So if b was 10 and a was 2, and I have 8 rectangles, then my delta x is going to be 1, because I would have 10 minus 2 over 8. Okay. As n approaches infinity, the sum of the areas of rectangles approaches the area under the curve. In other words, the more rectangles we have, the closer we're going to be to our actual area under the curve. And we can see an illustration of that here. On the left, this would be our A and our B. This would be our A and our B. Okay. Here, n is 3. The number of rectangles is 3. And here our n is 8. We can see that with the n being 8, we have very few gaps, and the gaps are very small. With n is 3, we have one very large gap right here and another very large gap here. And we have an overshoot right here and another overshoot right here. So we are a little bit farther off than we would be if we had more rectangles. Now, the other thing that we need to look at is where are the endpoints of our rectangles going? Okay, so I'm going to show you an illustration of what the 3 different types look like. We've been drawing right endpoints so far. So our right endpoints, we put the top right corner, oh no, let's fix that. Our top right corner of our rectangles was on our curve. So it looked something like this. And we can see that this, if we've got A to B, this here is an overestimate. Okay, I've got all these chunks that are extra above the curve, not the area under the curve. A little chunk here. If I do left endpoints, that means that the top left corner will go on our curve. So that's going to look something like this. And we can see that this would be an underestimate because I have these gaps where I did not fill in the area under the curve. I'm missing chunks of my area. So this is going to be an underestimate. The midpoint approximation is the best one, okay? And that's because it's going to have some bits that are under and some bits that are over. The middle of the top of your rectangle will lie on your curve. So if this is my A, and I want to draw my next rectangle here, this means that the middle of that top of the rectangle is going to go on my curve like this. So you can see we've got some little bits that are over and some little bits that are under, making this one just right. So we've got an over and an under, an over and an under, an over and an under, an over and an under. So it's almost like the over and under sort of balance each other out. Okay. So let's try some questions. We're going to find the area under the curve of y equals x squared from x1 to x4 using 3 approximating rectangles. And we're going to try it with each of these methods here. Okay, so we're going to start with the right endpoint. So the first thing we're going to need to do is sketch our curve. And this is a sketch, it's not going to be exact. And since we're going from 1 to 4, I'm going to go 1, 2, 3, 4. Okay. And it's y equals x squared, so I need to get all the way up to 16. I'm going to go 2, 4, 6, 8, 10, 12, 14, 16. And when I draw my curve, that means when x is 0, 1, 4, 9, 16. This is our y equals x squared. Okay. Now, we need to know what our delta x is for when we draw our rectangles because that's going to be the width of the rectangles. So remember, delta x is equal to b minus a over number of rectangles. So in our case, this is going to be 4 minus 1 over 3, which gives us 1. Our delta x is 1. That means our rectangles are going to have a width of 1. Now, a right endpoint means that if this is my a and this is my b, I'm going to have the right side of my rectangle touching the curve. So my width of my rectangle is 1. My height of my rectangle will need to be over here at the x value of 2. And so my rectangle is going to be drawn in like this. My next one, my width is 1, and my height, top right corner, is going to land on my curve like this. And then a width of 1, and my height, my top right corner will land on my curve. Now we want to actually figure out what the areas are. So my area is going to have to be delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3, because there are 3 rectangles. Delta x is 1. F of x1 is going to be 1 squared. Delta x is 1. F of x2, f of x1 is 2 squared, because this is x1, this is x0, x2, and x3. Okay, so f of x2, should be 3 squared, and f of x3 should be 4 squared. So my area is going to be 4 plus 9 plus 16, which gives me 29. For my left endpoint approximation, I'm going to draw my picture just a little smaller this time because I'm kind of running out of space. X, Y. So I still have 1, 2, 3, and 4. Okay, and I still have to go up to 16. I still need 0, 1, 4, 9, and 16. This time for my left endpoint approximation, my left top corner is going to go on my curve. So my width is still 1, but this time my top left corner will go on my curve when I draw my rectangle in, like this. Then my width is 1, but my top left corner will go on my curve. My width is 1, my top left corner will go on my curve. So in this case, my area is going to be 1 times 1 squared plus 1 times 2 squared plus 1 times 3 squared. Or in other words, 1 times 1 squared plus 2 squared plus 3 squared. This is my delta x, and this is my f of x0 plus f of x1 plus f of x2. Let's do this. Okay, that's what we essentially have here, which gives me 1 plus 4 plus 9, or 14. So we can see the 14 is an undershoot. We definitely are underneath the curve. We don't have enough space going on here to fill up underneath the curve here. We've got all these gaps here. Okay, and we can definitely see that the right endpoint here was an overshoot. We've got a lot extra. So we know that 29 is more than our area, 14 is less than our area. If we wanted to do a midpoint approximation, this means the middle of the top of each rectangle needs to go on our curve. So let's draw in our curve again. So we've got 0, 1, 4, 9, 16. All right, so our width is still 1, but this time the top middle of our rectangle is going to go in our curve. Now, when I do the area of this rectangle, it's still going to be delta x, but this time our f of xi is going to be f of 1.5, because halfway between 1 and 2 would be 1.5. Okay? Our delta x is still 1. Okay? Plus delta x, which is 1 times f of 2.5, plus delta x, which is 1 times f of 3.5. I still have 3 rectangles. Okay? The next one, I'm going to need to, again, put the middle of the top of my rectangle on my curve. And the last one, middle, top on my curve. So this is going to equal 1.5 squared plus 2.5 squared plus 3.5 squared, which should give me 20.75. So this, out of the 3, is the most accurate approximation for us. And again, this is because we've got a little bit over and a little bit under, a little bit over, a little bit under, a little bit over, and a little bit under. Okay. Now, the next one, we're going to try and use 6 approximating rectangles, and left endpoints is our estimate, an underestimate or an overestimate. So in this case, our 6 approximating rectangles, this means our delta x is going to change. We're going to have 4 minus 1 over 6, which means delta x is 0.5. Left endpoints means that I'm going to start at f of x of 0, which would be f of 1, because my a value is 1. So this should also be f of a. Okay. So when I do my area, I should have an area is equal to the sum of I equals 1 to 6, because there are 6 rectangles, of delta x times f of xi. Okay. So in our case, this is the same as delta x times the sum of all of our heights, which in our case is going to be 0.5. And then our heights, we're going to have 1 squared as our first one, because left endpoint. The next one, since our delta x is 0.5, is going to be 1.5 squared. Then the next one should be 2 squared, then 2.5 squared, then 3 squared, then 3.5 squared. And we keep going until we've got 6. We've got 1, 2, 3, 4, 5, 6, so we're done. And then we can actually figure out what this equals. It should equal 17.375. Okay. And this is also going to be an underestimate because if I were to draw my curve, looks something like this. And if we think about our left endpoints, they looked like this. We just have more of them. Okay? And we can see that we've got all these gaps underneath, meaning that we have a little bit less area than we should. And this is how we use our area methods, left, right, or midpoints, to approximate the area under a curve.